Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Anelen Sindane. The lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Our lesson for today is probability, and we are going to look at the terminology and the basic concepts that are done in grade 10. Now, at the end of the lesson, you should be able to understand the term probability. You should be able to compare relative frequency of an experimental outcome with the theoretical probability of the outcome. We should be able to use Venn diagrams as an aid to solve probability problems. And we should understand the concept of mutually exclusive events, complementary events, as well as exhaustive events. And we should be able to use the probability identity of any two events, A and B, which is given as the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now we can refer to the CAPS document on the highlighted pages and also on the grade 12 examination guidelines on page 7. Now, our pre-knowledge, we should be able to count. We should know what experiments are, and we should be able to know the definition of probability. We should be able to know the definition of an outcome. We should be knowing some of the tools we use in probability, our dice and coins, and we should have a knowledge of solving equations. Now, moving right ahead, we have our probability scale. Probability can be measured between 0 and 1, where we are saying if there's a probability of 0, our chance is 0, meaning it is impossible for that event to occur. If a probability is 1, we are certain that the event is going to occur. If the probability is 0.5, we have an even chance. We can also use our percentages or our fractions to represent a probability. For example, you are given a probability that if you rain in Gauteng as 0.3, that's in decimal form. As a percentage, we are saying there is a 30% chance that it might rain in Gauteng. For example, 2, the probability is given as a ratio, and we are told that the probability of contracting a flu virus is 70 to 100, meaning there is a 0.7 chance that you might get flu, or a 70% chance that you might get flu. Number 3, the chance of you winning a lotto, it's given by that. So meaning there is a 0.000007% chance of winning the lotto. Now, you have heard me using some words that are used with the term probability. You have a chance, likelihood. All those are terms that are used to represent a probability. As grade 12s now, we are busy. When we are asked questions, where will you be next year? Some are saying, I'll probably be at varsity. I will probably take a gap year. All those terms, we know that it's all about a chance. And hence, the term probability is used to represent as a measure of a chance or likelihood of an event occurring or not occurring. Now, by event, if you're asked a question, where will you be next year? So there is a chance that you'll be continuing with your studies at varsity. Some are saying there is a chance that they will take a gap year so that they relax, recollect their thoughts, and decide what to do next for their life. All those terms are part of probability, and we use these terms every day. And then I also have heard people, I am 110% sure. We say that in a way of exaggeration to say you are more than sure, but mathematically we cannot be more than sure. It's either it's impossible, it's even, or it's certain. We can only be 100% sure if we are certain that event is going to be occurring. Now, I've already mentioned that we can represent a probability using fractions, decimal, percentage, or a ratio. In short, we cannot have a probability which is more than 1, as we cannot be more than certain that the event is going to occur or not. In some instances, we are given statements where we are supposed to use the probability scale to predict or estimate or make a conclusion about a particular statement. If the statement is true, we can say the probability is 1. If the statement is not true, the probability is 0. Now, the other terms that are used with this, we have got terms like most likely, unlikely, very likely. So we use those terms also in our probability scale to estimate statements. For example, you may be given statements like this. What is the probability that it will rain today, the 10th of August, 2022? What would you say? What would you give as an answer for a probability? Now, we cannot say it will not rain. We cannot say it is a probability of 1 that it will actually rain. But we look at the season where we are in, it's winter, and it's very unlikely that it rains in August. So we can give a probability of about 0.25, 0.3, because it's very unlikely that it rains in August. So all these terms, you will see that you can use probability to answer true or false statements, or you can be using these to estimate statements that are given to you using the chance. Like I said, for me to make a conclusion about the rain today, I'll go outside. If there are no clouds and there's no sign that there are clouds that are building up, so I cannot say it's impossible that will rain, because the weather can change anytime. Hence, I said it is very unlikely that it rains. But I cannot say it's an even chance. I cannot say it's certain. I actually approximate to unlikely, which is between our 0 and 0.5 as an approximate estimation. The statement continues. The greater the probability, the more likely the event is to occur. Conversely, if there is a small probability, there is less chances that the event will occur. For example, the one that I use, that there is a 70 to 100 chance of contracting the flu virus, it's a strong probability. as you can see. And also, if you look at the chances that it is going to rain in Gauteng, we said it's a 30% chance. And for you to win a lotto, we saw that it's 0.000007% chance. So it's very unlikely. And there is no big chance that you can win. Let's define probability. We said it's a measure of chance or likelihood of an event occurring measured as a real number in the interval 0 to 1. I've mentioned we cannot have a negative probability. We cannot have a probability which is greater than 1. Hence, that interval is closed. It's between 0 and 1. And remember, as a percentage, it's between 0 and 100%. And as a decimal, it is between 0 and 1, as mentioned. Now, this is just an explanation. If the probability is 0, it's impossible, the event can't occur. If the probability is 1, it's certain. If a probability is 0.5, there is an even chance. For example, if I have a coin has two sides. If I toss a coin, it can either land on a head up or tails up. So there's an even chance that I can get tails if I toss a coin. So theoretically, we define probability as the number of outcomes of a particular event E over the number of outcomes in the sample space S. And the probability of an event E will be given by the number of times the event E occurs over the number in our sample space. So, in short, we are saying the probability of an event is between 0 and 1, where we are saying our probability of a null set of an event not occurring is 0, and the probability of the whole sample space is given as 1. We move on to probability branches. We have two branches of probability. We have theoretical probability. This one involves logical thought. I've given you an example of a coin. If I toss a coin has two sides, and the probability of me getting tails will be 1/2. Looking at the example of a 6-sided dice, the probability of getting a number 4 when you roll the dice, because there's only one 4 out of the 6 faces, so it becomes 1/6. Then we have experimental probability. This is a method that involves many trials. I'm yet to define what trials are, what an experiment is. Now, if we roll a dice 200 times, you will not get exactly 200 divided by 6. But as an example, if I roll a dice and you obtain a 4, it means you'll record every time you roll a dice, you record which sides it lands on, and you record the number of times that each one is obtained. So I'm saying theoretically, for example, if I roll a dice 200 times and I get 4 33 times, it means the experimental probability is going to be 33, the number of times that I'm obtaining a 4, over the number of trials that I've made, which is 200, and that will give us a probability of 0.165, and approximately to the 1 decimal place it will give us 0.2. And we know that in most cases our experimental probability gets close to our theoretical probability if we do as many trials as we can. And it is important that we always use a fair dice if we are using also a fair coin. So those are the terms that we normally use in probability. There should be fairness, so that we have an equal chance of any of the events occurring. Otherwise, if it's biased, we will not get the correct results. Also, for experimental probability, we use relative frequency. Relative frequency is the number of times a particular outcome is going to be obtained. Now, we look at the terms like a random experiment. This is a process in which physical actions are repeated many times to establish the frequency. I've talked about the frequency, the number of times that a particular event is going to occur. By random experiment, we are saying we cannot predict the outcome beforehand, hence it's a random experiment. For example, tossing a coin, it's a random experiment. Rolling a dice, it's a random experiment. If you are working with a spinner, you are spinning, it has different colors or numbers, you want it to land somewhere, all that, it becomes a random experiment because you cannot predict beforehand what the outcome will be. Now, I have given that example, you are able to read it. So each time you do a trial or you carry out the experiment, for example, each time you toss, we call that a trial. And each time you get a result, a coin lands after tossing, that becomes an outcome of that particular trial. And in this case, we record, for example, if it's a coin, head and tails. If it's a dice, you know the outcomes 1, 2, 3, 4, but 5, 6, but we count the number of times each lands. Now, the set of all possible outcomes is known as the sample space. And I will give an illustration using the coin tossing. There is a coin, it has a head and tails. So we are saying there are two possible outcomes, head or tail. So our sample space, we use set notation to represent our outcomes. And we are saying the number of outcomes in our sample space, we count them, there are 2. So that is the notation we use, number in our sample space, it's 2. And then experiment 2, you are rolling a dice and we record the number that appears. We know this dice and we are able to see the outcomes that may land on, and our sample space is given as that. And the number in our sample space becomes 6 because we have why it can land on a 1, on a 2, on a 3, on a 4, on a 5, or on a 6. So the number in our sample space will be 6. So probability, we don't want to write a lot of statements because us mathematicians are not good with statements. So we understand the shorthand that we use in this subject. So we use capital letters to represent our events. For example, E1, it's obtaining an outcome H. Now we are looking at theoretical probability. E2 is the event of obtaining tails. And then E3, we are saying it's getting either head or tails. E4, it's getting neither of those, which is impossible. If you toss, a coin has to land. It will never land on its edge. It has to fall on one side. Now, we are using our probability language. So I'm able to say the probability of getting heads, I can write it as PE1, the number in E1 over the number in my sample space. E1, it's getting a head. The number of times I can get a head, it's 1 out of a possible 2 outcomes. That's 50%. For tails, it is the same. For getting either or, that one becomes E3. It's either you get one of the two. So the number in E3, it's both head and tails. Hence, we will get a probability of 1. It's given. The probability of getting neither, it becomes 0 because a coin has to land. It's very rare that a coin will land on its edge and not fall on either side. Theoretically, we are now rolling a dice. A dice has 6 faces, as you can see there. And our sample space, I list all the possible outcomes, which are 1, 2, 3, 4, 5, 6. The number in my sample space will be 6. And the probability of getting a number smaller than 3, I know that the probability of getting a number less than 3, the probability of E, where E, it's 1 and 2. So the number in E, any number which is less than 3, I have 1 and 2. These are less than 3. Hence, the probability of getting a number which is less than 3 is going to be given by 2 out of 6, which will give us a probability of 1 over 3 when we simplify that. The probability of getting a 6, that's our event. E, it's getting a number 6. We only have one outcome where we have a 6, that one. It will give us a 6. And we are saying we only have one face that has a 6 out of 6 faces in our die, and that will give us 1 over 6 as the probability. So the probability of getting an even number, we know that even numbers, we know that we have got a 2, a 4, and a 6. Those are even numbers. They are exactly divisible by 2. So we are going to have our event as 2, 4, 6. Those are the possible outcomes over our sample space. So we are counting, it's 1, 2, 3 items over the sample space, which has 6 items. Hence, we have our probability as 3 over 6, which will give us 1 over 2 as the probability. Now, the probability of getting a number greater than 6, we are looking at the faces of a dice. There is no way we can get a number which is greater than 6. Hence, that becomes a null set, and we represent null set by a 0, which has a cross on it. That's a symbol for a null set. And we are saying, because there is nothing in that set, it's 0 over 6, and that probability will be 0. We move on now to other shapes that are used to represent our outcomes in probability. One of them is Venn diagrams. We also have tree diagrams, and we also have tables, which we call contingency tables or two-way tables. We are yet to look at those, but for now, we are going to look at Venn diagrams in detail. Now, a Venn diagram usually is, we use a rectangle to represent our sample space. Other shapes can be used, but according to the CAPS document, we are using a rectangle to represent our sample space. And we are also using circles to represent events. Other books are using different shapes, but for our purposes, we shall use a rectangle for our sample space and circles to represent our events in the given sample space. Now, you are going to see diagrams like this as we move forward. You can see that we have event A represented by that circle in the Venn diagram, and we have our rectangle to represent our sample space. Second diagram underneath, we are having a Venn diagram representing two events A and B that do not overlap. They are disjoint, they do not intersect. We are yet to describe the type of relationship that we are going to have on these Venn diagrams. I know I mentioned things like mutually exclusive. We are yet to discuss these, but I know you already know them. We move on. Now, if you are looking at the next Venn diagram on top, you are looking at A and B, but now there's an overlap there for the two events, and we say the two events are intersecting, meaning there's something in common there. And then if you look at the one underneath, we have two circles that are overlapping and they are shaded, meaning we want to look at all the outcomes that are covered under the shaded region, and we normally say it is the union of the two events, or we say it is P or Q. Everything that is under the shaded region covers what is there on both events. If you look at the next one, we only have one part which is shaded. You can see that the intersection is left blank. So you are going to be looking at this when we answer questions. Calculate the probability of P only, meaning that does not include the intersection or the overlap. So we are looking at the shaded region only in P, in set P only. And also the one underneath, you are looking at the set Q only. And then we also have the set that is given where it's shaded inside the sample space but outside the events. And we call that one not A or not B. In this case, it's not P and not Q. You are looking at all the outcomes that are not part of the events P and Q. So we look at the shaded area. So it's the not part. We will talk about it. And then if you look at the one underneath, we are having three events, A1, A2, A3. And only a small portion there is shaded. That is the intersection of all the three events. We shall deal with this mostly next week when we are looking at more than two events. Now, we also have that set where we have A1, A2, and those are shaded. It means it's A1 or A2 or A3. It's in any of the given three events there. And then if you look at the one underneath, you are having three events, but you only have A1 shaded without the intersection, meaning you are only looking at A1 only. Now, we have Venn diagrams which are used to represent. I just want us to look at this example that I have here. We are using Venn diagrams to represent probability outcomes. Now, I will use the example linked to rolling a dice. Our sample space when rolling a dice, we said our sample space will be S is equal to 1, 2, 3, 4, 5, 6. Those are our possible outcomes. If set A or event A, it's getting an even number, we are going to have that. And set B, it's getting a multiple of 6. You are aware that set A will have 3 outcomes and set B is going to have 4 outcomes. So I can write number in A is equal to 3. Number in B will be equal to 4. Now, let us look at what can we have on the intersection, which is the number in A and B. If we look at this information, let's look at set A. We are having a 2. Set B, we also have a 2. Now, we also have a 6. In set A, we also have a 6 in set B. So in short, the number in A and B, the ones that appear, it means it's 2. Now, but we want to check the number in A or B. How do we get the number that will be in A or B? I can draw my Venn diagram. And I will say my sample space is equal to 6 because I'm having 6 items in the sample space. My events A, I've seen that there's an intersection because of that end there. There are 2 items that appear in both sets. So I can have my set A, my set B with an intersection there. What do you realize? I will have in my set A, I start filling in from the intersection. So I will write my 2 and my 6 in that region where the 2 sets overlap. And then for set A, I'm left with the 4. I'll write the 4 there. For set B, I will write 1 and 3. Now, how many items do I have in the set A or B? I'm able to count 1, 2, 3, 4, 5. But my sample space must have 6 items. So meaning you are able to see that there is a 5 which is on the sample space, but it's not included in any of the events A and B. So we write it inside the sample space, but outside the 2 events, and would have come out with a Venn diagram to represent that information. So we are able to say the number in A or B, we are just counting 1, 2, 3, 4, 5. So the number in A or B will be given by 5. Now, if we start dealing with probabilities, we know how to calculate probability. So we say the number in our sample space is 6. So if I want to calculate the probability in A or B, it will be given by the number in A or B over the number in our sample space. So this will give us an answer of 5 out of 6. And then if I check also the probability of A, meaning we are just calculating the number in A over the number in our sample space, and that will give us 3 out of 6, which gives us half. The probability of B will be given by the number in B over the number in our sample space, and that will give us 4 out of 6, and that will give us 2 over 3 as a probability. Also, if you look at the probability in A and B, that will give us the probability as the number in A and B over the number in our sample space, which will give us 2 over 6, which simplifies to 1 over 3. Now, we want to find a quicker way of finding the probability of A or B, and this will lead us into something that is known as the probability identity that we have spoken about. Now, there is our outcomes, and we shall move on now to the probability identity. This, I will do it faster. This is what I had drawn in the previous slide, and you are able to see what is happening there. I've indicated these outcomes there. This one looks a bit neater, and we have seen the outcome. So we need to show that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, like that. Now, our sample space, we have it, and the number in A, we have represented these 3. I've done this part, you have seen it. And the number A or B, I've counted these and we got them as 5. And I've also shown you the probability of A or B. And then we said the probability of A or B will be given by 5/6. Remember, it's just brackets that are missing there. And we will get the probability as that. And if we will check the probability of A or B, we found out that it will be, I have indicated 3/6 plus 4/6 minus 2/6, and that gives us 5/6. Remember, when we counted, we said the probability of A or B, it will be 1, 2, 3, 4, 5 out of the sample space. It will give us 5 out of 6. So using this equation, you are able to see that the left-hand side and the right-hand side are equal to this 5/6. So it means this should hold all the time. Now, we shall move on now and look at the other concept that we are going to look at, which is the concept of mutually exclusive events. So remember, we are saying our probability equation PA or B is given by the probability of A plus the probability of B minus the probability of A and B. So this is an important identity that we are going to use now for grade 10 work, grade 11 work, and for our grade 12 work. Now, for mutually exclusive events, these are events that cannot occur at the same time. I'll give you an example of even and odd numbers. You cannot have an odd number which is also an even number. So those events are mutually exclusive. There is no intersection at all, meaning our set for A and B should always be 0. The number there should be 0. The probability should be 0 if we are having A and B as events or P and Q as events. It should always be 0 because there is no intersection. Now, we say there is no intersection, the probability of A and B is 0, and you will see that if we take this back to our probability identity, where there is and we are putting 0, meaning we are able to say that for mutually exclusive event, the probability of A or B will be given by that. Please, these are important. You have seen questions. They normally like this probability equation. It has to be there. And I will use the even number and odd numbers. You will find out that odd prime number, you are able to see that these will not intersect. We'll have two disjoint sets, and with a 1 in the sample space, because we are looking, 1 is not a prime number, though it's odd. So we should be careful as well when we are reading some of these statements, because that's how we get tricked. Remember, we did the definition of numbers in grade 10, so we must keep on revising and knowing them, because under probability, even when we do the grade 12 counting principle, we'll be dealing with codes and so on. We must be knowing the definitions of these numbers that we did in grade 10. We must know them and have them in our fingertips. Now, we want to look at exhaustive events. Now, you can see there are terms like union. Union, it's or. Intersection, it's a symbol like that, it's union. But according to KEPS document, we must use the terms or. We are teaching you this because some of the textbooks use these symbols. So this one, it's union, and the term that is used there, it's or. You must be careful. And we have this one where we have this symbol that looks like a U facing downwards, and this is the intersection. And for this intersection, we use the term and. We shall see as we move along. Now, the probability of A or B is always equal to 1. Now, the probability of our exhaustive events should be equal to the sample space, which is equal to 1. So, we combine this with the general rule. If A and B are exhaustive, it would mean that the probability of A plus the probability of B minus the probability of A and B should be equal to 1, because the probability of A or B is equal to 1. Exhaustive events. Now, the union of the two exhaustive events equals the sample space, and you will find out that this will always fill up the entire sample space. There is no space for writing any term outside one of the events there. These are exhaustive events. We shall look at them. We also have what we call complementary events. These are events that are mutually exclusive and exhaustive. Now, if A and B are complementary, we know that the probability of A and B should be equal to 0. The probability of A or B should be equal to 1. In short, the probability of A plus the probability of B should be equal to 1 from the probability equation. And we know that if A and B are complementary, then the probability of B is the same as saying the probability of not A. And we know that when we substitute, we are able to see where there is probability of B, we substitute with probability not A equals to 1. We can therefore conclude that the probability of A is equal to 1 minus the probability of not A. So if you are given the probability of A and these are complementary events, you are able to find the probability of not A. You add them, they give you 1. So if you are given 1, you are able to get the other. You will see as we do questions. So probability not A is 1 minus the probability of A, and the probability of A is given by 1 minus the probability of not A. And using a diagram, if you are given an event A, the shaded part is what we have as not A. And for our Venn diagrams, we can use probabilities or we can use the actual numbers of the outcomes that we are representing. Now, we are able to use the one where we said odd numbers and even numbers. You are able to see that A and B fill up the entire sample space, and there is nothing that is left outside those two sets. So A and B are complementary events. If a number is not odd, then it can be even. So they fill up the whole sample space. Now, we shall quickly start looking at questions now. I hope the theory is just to revise the grade 10 one. Please read and understand the question or scenario. Represent the given information in the form, e.g., if event A is this, are you looking at numbers or are you looking at probabilities? If it's numbers, then you represent number in set A or number green, number blue, depending on what you are dealing with. And then our sample space, we use capital letter S and N. Interpret the question extracting key information from the keywords like random experiment, mutually exclusive, complementary, exhaustive. You will know what to use. You can represent the outcomes using appropriate diagrams, e.g. Venn diagrams, or you can select the correct formula if there is formula to use, and you can substitute and answer the questions. Now, I'll give you 2 minutes to attempt this question, though it's given as an example. I just want to check if you were following. Just attempt this. I'll give you 2 minutes to try and see if we are moving together. 2 minutes. Let's work on this question. Welcome back. I hope we have managed to look at the kind of questions that we should expect in our examinations. Please also be aware that you can ask your questions on our WhatsApp line, and it's 064 748 and 8913. If you are having any questions that you need clarified, you can use our WhatsApp line. Let's go back to the question. 8.1, we are saying it's a random physical science experiment. We have two different events, A and B. The probability of getting event A is 2/5. The probability of getting not event B is given as 3/8. I have to mention this. The other symbol that we use for not B, you can use B with that prime on it. It means not B. And if it's just this, it means the probability of B, P plus P prime B is equal to 1. That represents not B. Now, calculate the probability of B, which is what we are expected to do. So, to calculate the probability of B, we are going to use complementary events. So, we know that the probability of B plus the probability of not B is equal to 1. In which case, this is going to lead us into saying the probability of B will be given by the probability of B will be given by 1 minus the probability of not B, in which case it will be 1 minus 3/8. Punch this on your calculator, you should get 5/8. So you'll get a mark for knowing the rule and substitution, and for the answer, P of B is that one. See, in maths, we don't like so many statements, as we are able to see that you are answering correctly the moment you write this. We want to find the probability of A and B. Remember our probability equation. It's given by the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. We can change the subject of the formula, and this will give us the probability of A and B will be given by the probability of A plus the probability of B minus the probability of A or B. Then we can substitute. Probability of A is 2 over 5. We have it there, plus the probability of B, we just calculated it. We found 5 over 8 minus the probability of A or B. We are given it's 5 over 7. We are given that one. And we can use our calculator. And that should give us the probability of A and B will be given by, if we do our subtraction, we should get 87 over 280. So that will be our answer. This question was allocated 3 marks. Using the equation, substitution, and answer, we get our 3 marks there. We move on to the next question. It says, this information will be the same, hence determine whether events A and B are, I will underline, mutually exclusive. Remember, for mutually exclusive events, we said the condition P, A, and B must be equal to 0. But if you check now, we just calculated in 8.11b, we calculated the probability of A and B, and we got our answer as 87 over 280, which is 0.31 something. Now, so are the events A and B mutually exclusive? Our answer will be no. And motivate your answer. We must give a reason why they are not mutually exclusive. The condition for mutually exclusive events, the probability of A and B must be equal to 0. So what we have here becomes our reason. We are going to say no, the probability of A and B is not equal to 0. So you will get an answer for no, a mark for no, and you also get a mark for calculating the probability and showing that the probability of A and B is not equal to 0, as we found it as 87 over 280. This is good enough. You don't need to write statements in English. We will understand as teachers and markers that you know the concept of mutually exclusive events. We move on to the next example. Yes. Now, for our exams, you will find out that sometimes you'll be given information represented in a Venn diagram, or you'll be given information and asked to come up with a Venn diagram. So we should be comfortable with either way. Now, there is the information and it's also represented in a Venn diagram. We are supposed to calculate the value of x, and we are also supposed to calculate the probability that if a boy is chosen at random, he does not play hockey or soccer. And B, we also have to calculate the probability that the boy plays only soccer. But I want us to attempt this question before we discuss it. We have the knowledge and I want us to try things as well to check if we are following on what we are doing. So I'll give you 3 minutes to attempt that question, all the questions there that are asked, because you already have the information and the Venn diagram done for you. So I'll give you 3 minutes. Let's attempt that whole question 8. Welcome back. I hope you have attempted the question. Now, we need to calculate the value of x. Now, remember, we can write our sample space is equal to 42. We write it on the top right corner, inside or outside, it's fine. And then we are able to see and interpret this Venn diagram correctly. And it is always safer for you to represent your information starting with the intersection. In this case, you are able to see that an unknown number of x play both soccer and, so it means that's our intersection. That's why we started with x. Remember, hockey, it's that red circle. It means if I add the number of players that play soccer and hockey, which is x, for hockey only, I must get the 27 minus those that are playing both, so that I'm able to get hockey only, which is what I have as the shaded region there. That's 27 minus x. And if I add 27 minus x plus that x, which also plays soccer, I will get that 27 that I have there. Also, if you look at soccer, if I add x plus 32 minus x, x plus 32 minus x, I must get the total number of soccer players, which in this case will be 32. So that Venn diagram is correct. But you see, we have 7 that do not play hockey or soccer. They are written inside the sample space, but outside the 2 events, which are H and S. Now, we are supposed to find the value of x. Remember, when we add all the events in all the totals in our events, including those that are not part of the events, they must give us our sample space. That's what we are going to use. So I'll write, we were not going to repeat anything. It will be 27 minus x plus 32 minus x plus the 7. This should give us our sample space, which is 42. Negative x plus x, this means here we'll get 0, and then we will only have negative x there. 27 plus 32 should give us 59. 59 plus 7, this should give us 66 minus x is equal to 42. We want to solve for x. If I take x to the other side, it will become positive, and 42 comes this side. I will have 66 minus 42, and this will give my x as 24. So you will come back, you indicate those values. So it means those that are playing both sports, it's 24. Those that are playing soccer only, it will be 32 minus 24, and that will give us 8. And those that are playing hockey only will have 3. And check, we are able now to see the number of those that play either hockey or soccer. Let's move on to the next question. Now I will move on the information to here. Remember, we said our x is 24. Our 32 minus 24, we got 8. 27 minus 24, we got 3. So that's the information that we are having. Calculate the probability that he does not play hockey or soccer. So it means we are looking at the region outside the 2 events, isn't it? So I'll shade that so that you are able to see where we get. Which number do we have? It's that 7. So we want to find P, not H or S. And that gave us, we are having 7. The number is 7 over our sample space, which is 42, and our answer becomes 1 over 6. That is the probability, not hockey or soccer. We are getting 1 over 6. We move on to the next question. It says the probability that he does not play soccer. Plays only soccer. Plays only soccer. And we looked at that one. So we want to find the probability of S only. So the probability of S only will be given by, we said for this question now, you are looking at inside S, but does not include the intersection. And we said it's 32 minus 24. So the number will be 8 over 42. And when you simplify this, we are going to get this as 4 into 8, we get 2. 4 into 42, it can't. It goes once, but in this case, we'll get our answer as 8 over 42. We can use 2. We'll get 4. 42, 21. So our answer will be 4 over 21 there when we simplify it. There are only 8 that only play soccer out of the 42 boys in that class. Now, I will give you this question to attempt very fast, and I will give you 4 minutes to attempt question 7. Let's attempt question 7.1, 4 minutes. We will mark it, and then I'll give you another activity to do. Right, welcome back. I hope you had a nice time doing this question. Now, for two events, it is given that the probability of A is 0.30, the probability of B is 0.65, and the probability of A or B is equal to 0.74. Now, calculate the value of A and B. So we must find a way of getting this. So we are given the probability of A, we are given the probability of B, we are given the probability of O. There's something which is going to assist us get our answer there. And that's our probability identity or equation, which is given by the probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. We want and, remember changing the subject, we are able to have probability of A and B is given by the probability of A plus the probability of B minus the probability of A or B. Now, so this one, it's a simple substitute and get an answer. We have 0.3 plus 0.65 minus the probability of A or B is 0.74. And if we add this one, we are going to get 0.95 minus 0.74, and that will give us 0.21 as the probability of A and B. So identity and substitution, we get 1 mark, and final answer, we get those 2 marks. Let's look at the next question. We're able to get that one, and we got it as 0.21. Now, we need to represent this information in a Venn diagram. So I'll carry on. We have calculated the probability of A and B, and we found it as 0.21. Now, please understand that when you are dealing with probabilities, your sample space will always be equal to 1. We explained this from the beginning when we said a probability scale is from 0 to 1, meaning if we are dealing with probabilities, our sample space will always be equal to 1 because probability is a fraction and we cannot have a probability which is more than 1. So let's check. So I will draw my rectangle and I will write my sample space is 1 because I'm dealing with probabilities. And if you check, there is an intersection, so my events A and B must overlap. And remember, whenever you are filling in information from the Venn diagram, for you to be accurate, always start filling in information from the intersection. In this case, our intersection, the probability is 0.21. Now, for event A, we must get a total probability of 0.3. So, if I subtract, for me to get the probability of A only without the intersection, I must say 0.3 minus the intersection, which is 0.21. It should give me 0.09 there. And the probability of B only must give me 0.65, which is the probability of the whole event B. It's 0.65, and I subtract 0.21, and that should give me 0.44. And if I add these, they must give me A or B. Remember, if I add 0.09 plus 0.21 plus 0.44, I must get 0.74. if my calculations are correct. And it gives me that because this gives me 0.3 plus 0.44, I'll get 0.74. But my sample space must give me 1. So it means outside the two events, I will say 1 minus 0.74, and that will give me 0.26, meaning the probability of not A or B is going to be 0.26. And if I add all the probabilities within the rectangle, I'm getting a 1, 0.09 plus that, I got 0.30 plus 0.44, I get 0.74 plus 0.26, I'll get my sample space, which is 1. So when we mark the Venn diagram, it has a 0.1, intersection 0.22, 0.4, and the 0.26 outside. It must be a proper Venn diagram, then you will get your 4 marks there, as you can see. We move on to the next question, 7.13. Are the events A and B mutually exclusive? Give a reason for an answer. This, we have seen it before, and you can see examiners like it. So our answer, A and B are not mutually exclusive. Your reason, it's because the probability of A and B is not equal to 0. We found it as 0.21, or you can say there is an intersection as your reason there. So no, PA not equal to 0, so you'll get a mark for no and a mark for probability not equal to 0. We move on to the next activity. This one, I'll give you 1 minute. 1 minute. Let's quickly attempt. Welcome back. This was an easy one. Now you are looking at the word algebra. So our sample space, in this case, number in our sample space, you count the number of letters. It's 1, 2, 3, 4, 5, 6, 7. And then you want to find out what is the probability that a chosen letter is. So these letters can be given in the form of cards you are just choosing. So the probability of getting the letter A will be given by how many A's do we have? 1, 2. So this will give us 2 out of 7. That's the probability that we have. Now, so you'll get 1 mark for that. 2 out of 7. What is the probability that the letter chosen is a consonant? English. Do you know what a consonant is? So the probability of getting a consonant. A consonant, these are letters that are not vowels. So in this case, how many letters are not vowels? We have got L, G, B, and R. So there are 4. So the number of letters that are consonant, number of letters that are consonants, we are going to have 4. So the probability of picking a letter that is a consonant becomes 4 out of 7. So that's your answer for that one. We move on to the next question. Yes, there is question 7.2. I'll give you 6 minutes to answer. No, let me give you 4 so that we have time to mark it. I'll give you 4 minutes to read and answer that question number 7. Let's quickly answer that question number 7. Welcome back. I hope you had a good time doing this question. Now, let's check. we are given our information there. It says 30 learners in grade 10. So we are able to say R represents right-handed. So number that are right-handed, it's 5. Number that plays soccer, NS, is going to be, in this case, it's going to be 12. And then number of learners who play soccer, so number R and S, it's going to be 3. And then we are supposed to draw a Venn diagram to represent the above information. So I will draw my rectangle to represent. So I will now use number in class. We are saying they are 30. And then I will have right-handed, play soccer. There is an intersection because we have 3 learners who are right-handed and also play soccer. Remember I said we start filling in information from the intersection. We have 3 learners here. In the whole circle of right-handed, I must get a total of 5. So what is 5 minus 3? It means I have 2 learners who are right-handed only and do not play soccer. On the soccer side, I have 12 learners that play soccer, meaning the whole circle for soccer must have a total of 12, meaning, but I have those 3 that are right-handed as well as play soccer, so it means here I'll have 9, so that if I have 3 plus 9, I must get the whole circle for soccer must have a total of 12. Now, let's check. 2 plus 3 plus 9, it means those that are right-handed and also play soccer, we have a total of 14, but the class has 30 learners, so meaning 16 are outside the 2 events. So it means those 16 are left-handed. They are not right-handed and they do not play soccer. Now, we are going to get our 5 marks for the sample space being 30, our rectangle for our sample space and our circles for that. So for that 2, 3, 4, that you will get your 4 marks. And then for the Venn diagram with a sample space, you will get the 5th mark. We move on to the next question. As you can see there, we are supposed to calculate, are the events play soccer and right-handed mutually exclusive? Remember, the answer will be no. For mutually exclusive, the probability of S and right-handed should be equal to 0. And also the number S and right-handed should also be 0. But in this case, we have 3 players that are playing soccer and are right-handed. So the answer is no. So the reason is the probability of R and S is not equal to 0, or you will say there's an intersection between playing soccer and right-handedness. We move on now to questions. So for the answer no and for the reason, you get the 2nd mark. Now we move on to the next question. How many learners in the class are left-handed and do not play soccer? Remember, we said there are 16 players that are outside. So the number left-handed, or would say number not right-handed and not playing soccer, will get 16. We get the 16 from our Venn diagrams, the ones that are outside. You'll get your 2 marks there. We move on now to the next question. It says, determine the probability that Elena is left-handed and plays soccer. The probability that Elena is left-handed and plays soccer. Remember our Venn diagram. Under playing soccer, we have 9 learners that are playing soccer only, and they are not right-handed. So meaning the probability of Elena is left-handed and plays soccer, you will take the shaded part there, which is the probability of not right-handed, it will be that, and plays soccer, it will be given by 9 over the sample space, which is 30, and that will give us 3 out of 10 as the probability. Now, you can take a photo of that question 7.1. You will do it later on as a homework. There are the solutions. You can also have 7.2. It requires us to draw a Venn diagram. You can also do it later on as a homework. That's 7.2. And we will do this during our spare time. And then I had also selected that as our homework. You can take a photo, and those are the solutions. Now, I hope we have learned something today, that probability is a measure of chance or likelihood of an event occurring. And we know that our probability scale is from 0 to 1, and we cannot have a negative probability or a probability which is greater than 1. And we also know that we saw that we can use probability to answer true or false statement. If the statement is true, you can use a probability of 1, and if it's false, it's a probability of 0. We also looked at mutually exclusive events, and these are the events that cannot occur at the same time. And we also looked at the probability equation, and we found out that for any 2 events, the probability of A or B will be given by the probability of A plus the probability of B minus the probability of A and B. We also used one tool to solve probability problems, and we have used the Venn diagram in this case. And we know that for the complement of any events, these are events that consist of, that fill up the whole sample space. The probability of A and the probability of not A, we have seen that it is equal to 1 minus the probability of the other. And we saw that for exhaustive events, they together fill up the entire sample space. We will continue with some of these concepts in our next lesson. I hope you have learned something today. Enjoy the rest of your afternoon, and let's continue to study, practice, and be safe, so that probably next year we are at a university pursuing the careers that we want to achieve. Have a good afternoon. I thank you.